Respected Des, here I am presenting about recycling COVID-19 pandemic waste towards triboelectric touch sensor for smart IoT applications. Here it is the contents. Coming to the introduction, Earth's plastic pollution has increased due to the COVID-19 pandemic, and the Earth is on the doorstep of an enormous waste pandemic. The extensive use of mandatory personal health protectives like face masks, hand gloves, and PP kits, and the lack of proper waste management systems led to a rise in the plastic pollution content of the earth. These distributed waste pollute land, soil, and water bodies and affect their ecosystems. According to the World Economic Forum reports, 129 billion face masks and 65 billion plastic gloves are being used and thrown away every month in the world. Some pathetic visuals of the pollution threats caused by the masks and gloves on the ocean, underwater, canals, coastal areas, paddy farms, ecosystems, and land are shown in the figure. Here, one fish stuck inside a disposed glove. This research work establishes the concept of a waste to energy conversion approach to reuse COVID 19 scraps for green sustainable development. Here in this work, the three layered face mask and nitrile gloves were used after sterilization for energy harvesting and sensing applications based on triboelectric nano generators. Coming to the detailed analysis on materials, there are variety of masks and gloves are available in the market. Here we selected three-layer mask and nitrile glove. Three-layered masks are made from polypropylene nanofibers. It has an outer hydrophobic layer to repel droplets and moisture, and inner light colored hydrophilic layer to absorb droplets from exhaled breath, and a middle filter layer. The inner and outer layers are made of non-woven spun-bound polypropylene and the middle layer with melt-blown polypropylene. The exact analysis of these three layers were examined in the 2 theta range of 10 to 30 degree, and it was noticed that the characteristic diffraction peaks alpha 110, 040, 130, and 131 are which are similar to the XRD of neat polypropylene. Here the figures C, D, and E are the scanning electron microscopic images of the surface of the mask layers. These nanofiber networks on the mask layers contribute high contact frictional surface area and increased surface charge density. This three-layer mask is a promising candidate for higher performance triboelectric negative material, because polypropylene is a electronegative dielectric material with high charge affinity and mechanical polarization. Then nitrile gloves are made of synthetic material called nitrile butadiene rubber NBR. Some image of nitrile glove as shown in figure G shows roughness on its surface. Nitrile glove is a promising candidate for triboelectric positive material because it has positive charge affinity, relatively high dielectric constant, high frictional coefficient, and high chemical resistivity. And also it is flexible material with a strong polarization. Using these three-layer mask and glove, we have fabricated a contact separation triboelectric nanogenerator named MGCS10. For that, a 3D printed framework was made which has an upper and lower part. A piece of copper coated mask was fixed on the upper part, and a piece of aluminum coated uh, a piece of aluminum coated glove were fixed on the lower part. These copper and aluminum act as top and bottom electrodes. Conductive wires were connected to these electrodes to make a connection with the external circuits. A metallic spring was inserted between the upper and lower parts so that the top and bottom parts can join and the device can press and release easily. While pressed, masks and glove will come in contact with each other and electricity will be generated. Then coming to the working principle, triboelectric nanogenerators can convert low frequency mechanical motions into electricity. It works based on the combined theories of contact electrification and electrostatic induction. When two dissimilar materials with opposite electron affinities come in contact with each other, a transfer of ions will occur between them. It is called contact electrification or triboelectrification. It is a surface phenomenon. Material that lose electron become positively charged and that gain electron become negatively charged. The amount of charges transferred depends on many parameters like nature of materials, their surface properties, friction between them, amount of force applied. When these charged materials are separated, there will be an induction of opposite charges on the attached electrodes. It is called electrostatic induction. The electrode attached to the negatively charged mask will induce positive charge and the electrode attached to the positively charged glove will induce negative charge. The potential difference between these electrodes causes the current to flow through the external circuit between the electrodes. Thus, a periodic form of AC output voltages and current will be obtained across the terminals due to the continuous contact and separation between these mask and glove. The generated voltage or current signals can be further utilized for energy harvesting or sensing applications. Simulation analysis of MGCS tank using console multiphysics software were performed to visualize the potential distributions and the surface charge on the materials. The electrical performance of the device were tested for different compressive forces. It could generate a maximum peak to peak open circuit voltage of 50.7 volt and a short circuit current of 4.8 microampere corresponding to a maximum applied force of 9 Newton. And it was observed that the both open circuit voltage and short circuit current were increased with the applied force. The device was connected to bridge rectifier and a capacitor to test its capacitor charging performance, and it could charge up to 1 volt within 10 seconds. Output voltages and currents were measured for different load resistances ranging from 1 mega ohm to 120 mega ohm, and then multiplied the instantaneous values of voltage and current to obtain the instantaneous value of power and the power density. For this device, it obtained a maximum power of 57.5 microwatt and a power density of 6.39 microwatt per centimeter square at 45 mega ohm load resistance. A stability test was carried out for 10 successive days to test the durability of the device and observed the output voltages to around 50 volt every day. Practical real-time application of MGCS tank were demonstrated in two ways to validate its performance. First one as energy harvester for powering electronic gadgets, and the second as a touch sensor for IoT cloud supported smart hand sanitizer dispenser. AC signal generated by MGCS time converted to DC and could power tally counter, wristwatches, Lumex display, and 25 series connected LEDs. To demonstrate as a touch sensor, MGCS10 was connected to Node MCU ESP8266 microcontroller and interfaced with a N-channel MOSFET and solenoid valve. And it integrated with Blink Cloud and Internet of Things. Here the MGCS10 was operated as a pedal. MGCS10 was acted as a pedal operated touch sensor. While it pressed, the microcontroller will trigger to open the valve and it will dispense sanitizer. The real-time data like voltage generated on each press, sanitizer usage count, sanitizer volume were uploaded to the Blink cloud using uh, Internet of Things or Internet access so that the authorized person can access the data and can monitor and control the sanitizer dispenser from any remote locations. The microcontroller can send alert messages to the authorities when the sanitizer volume goes below a threshold level. These are the videos. Then coming to the conclusion, here in this work, we reused COVID-19 pandemic waste like masks and gloves for real-time energy harvesting and sensing applications. By doing further material modifications and by using the different modes of triboelectric nanometer, its application range can be extended. These are the reference. Thank you.